Somewhere out there is a sky that looks nothing like ours, a sun that rises slower or faster, or perhaps not at all, a world where rain falls as something other than water, where the horizon bends at a different angle, where the stars, on a clear night, are not the same stars, and perhaps, just perhaps, where the air is breathable, where the ground is solid beneath your feet, where life, in some form, already exists, or is simply waiting. For most of human history, this question, is there another world that could be home, lived only in mythology, in dreams, in the minds of philosophers who had no instruments to look for answers. We have instruments now, more powerful than anything ever built. Telescopes floating in the cold of space, arrays of dishes listening across continents, algorithms processing light that has crossed hundreds of light years to reach a detector the size of a human hand. And the answer we're getting back is complicated, beautiful and humbling and strange, because the universe is absolutely full of planets, billions of them, trillions perhaps, orbiting almost every star you've ever looked at in the night sky. Rocky ones, icy ones, gas giants, water worlds, lava planets, diamond planets, a diversity so extreme that Earth begins to look like just one very specific solution to the problem of being a planet. But out of all of them, out of the thousands we've confirmed, and the billions we know must exist, how many could actually support a human life? That is the question this video is about. And by the time we're done, you'll understand just how miraculous and just how lonely the Earth might really be. Before we go looking, we have to define what we're looking for, because livable is not a simple word. For humans specifically, not microbes, not extremophiles, not hypothetical alien biologies, the requirements are surprisingly precise. Temperature, first. The surface must be warm enough for liquid water to exist, somewhere between roughly 0 and 100 degrees Celsius at standard pressure. Below that, water freezes. Above it, water boils away. And liquid water is not optional. Every biochemical process your body runs depends on it. Every enzyme, every cell division, every thought you've ever had has happened in the presence of liquid water. But temperature alone isn't enough. That temperature must be stable, consistent. Earth doesn't just happen to have the right average temperature. It has had a remarkably stable climate for billions of years. Stable enough for life not just to appear, but to evolve, diversify, and eventually build telescopes. Then there's atmosphere, breathable air, a specific mix of nitrogen and oxygen at the right pressure is the environment your lungs are built for. Too thin, and your blood boils in your veins at low altitudes. Too thick, and the pressure crushes you. Too much carbon dioxide, and every breath is poison. Too much of the wrong radiation, and your DNA degrades faster than cells can repair it. And then gravity. Too weak, and an atmosphere drifts away into space over geological time. Too strong, and standing, breathing, and pumping blood against the weight becomes a physiological ordeal your cardiovascular system was never designed to handle. And then radiation. A planet needs to be protected from the constant bombardment of high-energy particles, cosmic rays, stellar flares, ultraviolet radiation that would otherwise sterilize its surface and damage the DNA of anything trying to live there. On Earth, we have a magnetic field for that, generated deep inside our planet by the churning of liquid iron in the outer core, an invisible shield extending tens of thousands of kilometers into space, deflecting the solar wind that would otherwise strip our atmosphere bare over millions of years. This is what livable means. Not warm enough, not just wet enough, but the entire combination, sustained, all at once, for long enough to matter. Finding all of that in the same place, at the same time, is far harder than it sounds. Here's something that rarely gets said clearly enough. Earth is not the obvious outcome of planetary formation. It is not what you get when conditions are broadly right. It is a specific, somewhat improbable combination of factors that happen to converge on this one rocky ball in the inner solar system. And we are only beginning to understand how many of those factors matter. Start with our location. Earth orbits the Sun in what astronomers call the circumstellar habitable zone, the range of distances where a planet with the right atmosphere could have liquid water on its surface. Not too hot, not too cold. The Goldilocks zone. But Venus also orbits near the inner edge of that zone. And Venus, today, has a surface temperature of approximately 465 degrees Celsius, hot enough to melt lead, hot enough to roast a spacecraft within hours of landing. Not because Venus is too close to the Sun, it's only marginally closer than Earth, but because of runaway greenhouse warming that turned its thick carbon dioxide atmosphere into a planetary oven. Mars sits at the outer edge of the habitable zone, and Mars today has an average temperature of -60 degrees Celsius. Its atmosphere is less than 1% the pressure of Earth's, so thin that liquid water can't exist on the surface at all. It immediately either freezes or evaporates, and Mars has no global magnetic field. Cosmic radiation reaches its surface largely unimpeded. Earth is in between. But it isn't just position that saved us. It's the Moon. Our unusually large Moon, formed from a collision so violent it nearly destroyed the early Earth, stabilizes our planet's axial tilt. Without the Moon's gravitational steadying, Earth's tilt would wobble chaotically over thousands of years. Seasons would become extreme. Ice ages would be catastrophic. The climate that allowed complex life to evolve in relative stability for hundreds of millions of years might never have happened. It's plate tectonics, the churning of Earth's crust, driven by internal heat, continuously recycles carbon dioxide from the atmosphere back into the rock and back out again through volcanic activity. A thermostat operating on geological timescales that has kept Earth's temperature within livable bounds for billions of years. Mars and Venus show no evidence of active plate tectonics today, and both of them are, by any human standard, completely uninhabitable. It's our position in the galaxy. We orbit at a comfortable distance from the galactic center, far enough from the intense radiation and stellar crowding of the core, close enough to regions where the heavier elements needed for rocky planets exist in abundance. The galactic habitable zone is a real concept, and Earth sits within it. All of this before we've even left our own solar system. Earth is not ordinary. It is a very specific, somewhat stacked set of conditions that we didn't appreciate until we started finding other planets and realizing how different they all are. If humanity were forced to choose a second home within reach of current technology, the answer is Mars. Not because Mars is comfortable, it isn't. Not because Mars is easy, it won't be. But because Mars is close, a journey of 6 to 9 months at current spacecraft speeds. And because Mars, despite everything working against it, has more going for it than anywhere else in the solar system. Mars has a day almost identical in length to Earth's, 24 hours and 37 minutes. It has seasons because its axial tilt is similar to ours at about 25 degrees. It has a solid surface, not a gas giant, not an ocean, but actual ground to stand on. And beneath its surface, and locked in its polar ice caps, Mars has water, not liquid. At the surface pressure Mars has, liquid water can't exist, but frozen, waiting. Its gravity is 38% of Earth's. That's less than ideal. long-term exposure to Martian gravity would likely degrade bone density and cardiovascular function in ways we don't fully understand yet, but it's vastly better than microgravity. The human body might adapt, might not, might need artificial support systems. These are engineering problems, not fundamental impossibilities. The atmosphere, 95% carbon dioxide, less than 1% of Earth's pressure, cannot be breathed and provides almost no protection from radiation. Cosmic ray exposure on the Martian surface is roughly 40 to 50 times higher than on Earth's surface. Not instantly lethal, but enough to meaningfully increase cancer risk over a lifetime, and potentially enough to cause serious health problems over decades without shielding. Living on Mars for the foreseeable future means living underground, or inside heavily shielded habitats, or beneath meters of regolith piled onto structures for radiation protection, not stepping outside for a casual walk without a pressurized suit. Could Mars be made more habitable over very long timescales? In theory. Warming it, thickening its atmosphere, releasing frozen gases, perhaps even restarting some form of magnetic field, a process called terraforming. But terraforming Mars, even with technologies we don't possess today, is a project measured in centuries at minimum, more likely thousands of years. Mars is not a second Earth, not yet, possibly not ever, for a very long time, but it is the most achievable answer to, can humans live somewhere other than Earth? And serious planning is underway. Now we leave the solar system behind entirely. Because if we want to find a planet that is genuinely Earth-like, not Mars, not a compromise, but a world with breathable air, liquid water, a protective magnetic field, and conditions under which humans could conceivably live without elaborate artificial support, we have to look at the stars. And this is where the story changes completely. As of 2025, astronomers have confirmed more than 6,000 exoplanets, planets orbiting stars other than our Sun. 6,000 confirmed. And estimates suggest that the Milky Way alone contains hundreds of billions of planets. Most stars have them. Planets are not rare. They are, it turns out, essentially universal. The question is, what kind of planet? Most of what we found in the early decades of exoplanet astronomy is not what we were looking for. Gas giants orbiting impossibly close to their stars, so-called hot Jupiters, scorched worlds of no interest for habitability, mini-Neptunes. Super-Earths that are too large to be rocky and too small to be gas giants, their true nature unclear. Planets orbiting so far from their stars that they're permanently frozen. Planets so close, they're perpetually molten. Finding the small, rocky, temperate ones, the ones that might actually look like Earth, is hard. Not because they don't exist, because they're small. And small things are difficult to detect from tens of light years away. But the technology is catching up, fast. In 2026, we confirmed over 6,000 exoplanets total. Missions like NASA's TESS, the Transiting Exoplanet Survey satellite, have been cataloging thousands of candidates. The James Webb Space Telescope, launched in 2021 and now operating at full capacity, can do something no prior telescope could. Examine the atmospheres of rocky planets orbiting nearby stars. And in March 2026, a team at Cornell University published a landmark study. They went through all 6,100 known exoplanets at the time, every one, and applied a rigorous set of criteria: rocky composition, habitable zone orbit, stellar energy levels between what Venus and Mars receive from the Sun, and additional physical parameters. The result? 45 planets out of 6,000. 45 candidates that might be genuinely habitable. Let's look at the most compelling ones. In 2017, astronomers announced something extraordinary: a small, dim red dwarf star called TRAPPIST-1, named after the telescope in Chile that first studied it, was found to have not one, not two, but 7 rocky planets orbiting it, all of them roughly Earth-sized, all of them with densities consistent with rocky composition, and 3 of them, TRAPPIST-1d, E, and F, orbiting within the system's habitable zone. 3 potentially habitable worlds in the same star system, 41 light-years from Earth. The scientific world reacted with barely contained excitement. TRAPPIST-1 became the most intensely studied planetary system outside our own, and it remains, today, one of the most important systems we've ever found. But every time we look closer, the picture gets more complicated. TRAPPIST-1 is what astronomers call an M-dwarf, a red dwarf star. These are by far the most common type of star in the Milky Way. They burn cool and dim, living for trillions of years, far longer than stars like our Sun. And because they're small and dim, their habitable zones are very close in. TRAPPIST-1's habitable zone planets orbit their star at distances that, in our solar system, would place them closer to the Sun than Mercury. That proximity creates a serious problem: tidal locking. When a planet orbits so close to its star, the star's gravity tends to lock the planet's rotation to its orbit, the same way the Moon always shows Earth the same face. One side of TRAPPIST-1e would be in permanent daylight, perpetually facing the star. The other side would be in permanent darkness, cold enough to freeze any atmosphere that tried to migrate there. That doesn't automatically mean life is impossible. The terminator line, the boundary between the permanently lit and permanently dark hemispheres, might be a region of complex weather, flowing winds, and moderate temperatures. And a thick enough atmosphere could redistribute heat from day to night side, potentially creating a planet-wide zone of habitability. But there's another problem. TRAPPIST-1 is active, prone to powerful stellar flares, sudden eruptions of radiation that blast its nearby planets with ultraviolet and X-ray radiation. Flares far more intense relative to the planet's distance from the star than anything Earth typically experiences from our Sun. If any of the TRAPPIST-1 habitable zone planets still has a substantial atmosphere, those flares are a constant threat to stripping it away over billions of years. So the critical question, the one everything else depends on, is: do the TRAPPIST-1 planets have atmospheres? This is where the James Webb Space Telescope becomes the most important tool in this search. Webb can do something extraordinary. When a planet passes in front of its star, a transit, Webb can capture the starlight that filters through the planet's atmosphere, if it has one. Different gases absorb different wavelengths of light in precise, unique patterns. Webb can detect those patterns from tens of light years away. The news from TRAPPIST-1 so far is sobering. TRAPPIST-1b, the innermost planet, the furthest inside the habitable zone, really Venus-like, shows no evidence of a thick atmosphere. The Webb data suggests it may be a bare rock or have only a very thin atmosphere at most. TRAPPIST-1c, the second planet, also inside the habitable zone's inner edge, similarly shows no evidence of a substantial atmosphere. 2 planets examined and 2 strikes. But here's the crucial thing. These are the planets least likely to be habitable. They're the hottest, the most intensely irradiated. The more interesting candidates, TRAPPIST-1d, E, and F, sitting deeper in the habitable zone, are harder to observe and have received less Webb time. TRAPPIST-1e is the most promising of them. In 2025, JUIC's first spectroscopic look at TRAPPIST-1e came back without a definitive answer, but crucially, it did not rule out an atmosphere. it specifically permitted nitrogen-rich atmospheres with traces of methane and carbon dioxide, the kind of atmosphere that, broadly, resembles a version of early Earth. It's not confirmation, it's not even close to confirmation, but it's not a dead end either. The answer for TRAPPIST-1e is still genuinely open, and astronomers are planning more observations, more Webb time, more precision. The question of what's above the surface of TRAPPIST-1e is one of the most important unanswered questions in all of modern science, and we may have a real answer within this decade. Of all the exoplanets on the 45 candidate list, one stands apart in a very specific way. It is the closest, by a significant margin. Proxima Centauri b orbits Proxima Centauri, the nearest star to our Sun, at a distance of just 4.24 light-years. In the context of our galaxy, that is essentially next door. If every light-year were a kilometer, Proxima Centauri would be about 4 kilometers away. The galaxy would be 100,000 kilometers across. The planet was discovered in 2016, and its basic properties are remarkable. Rocky, mass estimated at around 6% more than Earth's, close enough that surface gravity would feel familiar. It orbits within Proxima Centauri's habitable zone, but Proxima Centauri is also an M-dwarf, and it has all the problems that come with that. It is one of the most flare-active stars known. In 2019, astronomers recorded a superflare from Proxima Centauri that was, for its duration, 14,000 times brighter than the Sun in ultraviolet. The kind of event that could strip a planet's atmosphere, damage DNA, and irradiate a surface to levels hostile to almost any life we know of. And these superflares are not rare occurrences. Proxima Centauri produces them regularly. Proxima b almost certainly has a tidally locked rotation, one face baking in the star's light, the other permanently cold. And unlike TRAPPIST-1e, we have essentially no data on Proxima b's atmosphere. Its geometry, relative to Earth, makes transit observations extremely difficult. Webb cannot easily examine it the way it can TRAPPIST-1's planets. So we have the closest exoplanet in the habitable zone of its star, and we know almost nothing about what it's actually like. Its proximity makes it the most compelling target for future exploration. The Breakthrough Starshot initiative, which aims to send tiny laser-propelled spacecraft to Alpha Centauri at 20% the speed of light, would pass Proxima Centauri and could potentially image Proxima b within our lifetimes. But for now, it is a dot of data, a gravitational signal in a star's wobble, and a name on a list of 45. Let's look at what the Cornell Project Hail Mary study of March 2026 actually found, when it went through every confirmed exoplanet and asked which ones are genuinely worth investigating for habitability. The study was deliberate in its methodology. The researchers used our own solar system as a calibration tool, identifying the range of stellar energy that Venus, Earth, and Mars receive, and excluding planets that fall outside the Earth to Mars range. Too much stellar energy and you risk runaway greenhouse warming like Venus. Too little and you risk a frozen wasteland like Mars. Of the 6,100 exoplanets analyzed, only 45 made the cut as rocky, habitable zone candidates. That's less than 1%. A universe full of planets, and the fraction that might actually work for us is vanishingly small. Among the 45, some familiar names: Proxima Centauri, b TRAPPIST-1e, and F, Kepler-186f, a planet orbiting a cool orange star about 580 light-years away, in the outer edge of its star's habitable zone, roughly the size of Earth. Kepler-442b, slightly larger than Earth, orbiting a cooler than our Sun's star, about 1,200 light-years away. receiving about 70% of the sunlight Earth does. One of the highest habitability scores ever calculated, and newer additions. GJ251c, discovered in November 2025, orbiting a red dwarf just 18 light-years away in the habitable zone, with a mass a few times larger than Earth. And GJ3378b, confirmed in July 2026, orbiting a star about 25 light-years from us, receiving almost identical stellar energy to Earth, with a mass just over twice Earth's, 25 light-years. In cosmic terms, practically a neighbor. What all 45 of these candidates share is a position in the right region around their stars. What most of them lack, because we simply haven't been able to measure it yet, is confirmed atmospheres, confirmed liquid water, confirmed magnetic fields, confirmed geology. We have addresses. We don't yet have floor plans. Here is the part of this story that no amount of excitement about exoplanets can make comfortable. The nearest of these 45 candidates is 4.24 light-years away. 1 light-year is approximately 9.5 trillion kilometers. 4 light-years is about 38 trillion kilometers. At the speed of the fastest spacecraft ever launched by humanity, the Parker Solar Probe, which reached speeds of about 690,000 kilometers per hour in its closest approaches to the Sun, reaching Proxima Centauri would take roughly 6,300 years. 6,000 years. That is longer than all of recorded human history. The breakthrough Starshot concept, tiny laser-sail spacecraft accelerated to 20% the speed of light by a massive ground-based laser array, would reduce that travel time to roughly 20 years, an extraordinary achievement if it can be built. But these would be gram-scale probes, not life support systems, not human-rated vehicles, not colony ships. Sending a human being to even the nearest exoplanet within anything like a human lifespan would require propulsion technology that doesn't exist today and may not exist for generations. Generation ships, vessels where the passengers who arrive are the grandchildren of the passengers who departed, are not merely science fiction. They are the most technically feasible option currently imaginable, and even they are centuries away from engineering reality. The 45 candidates on Cornell's list range from 4 to roughly 100 light-years away. Even the closest demand a level of propulsion technology that represents perhaps the greatest engineering challenge in human history. But here's the thing about engineering challenges. Humanity crossed oceans before it knew what was on the other side. It broke the sound barrier before it understood supersonic aerodynamics in full. It landed on the moon with computers less powerful than the one in a cheap digital watch. The gap between impossible with current technology and impossible is not nothing. It is where the future lives. The situation is not static. The tools we have today, impressive as they are just the beginning of what's coming. The Nancy Grace Roman Space Telescope, NASA's next great observatory, has an official launch date of August 30th, 2026. Its wide-field infrared camera will survey enormous swaths of sky, and scientists expect it to discover more than 100,000 new exoplanets in its first 5 years alone. 100,000 new worlds, each one a new address, each one a new candidate for the question we're asking. Webb will continue characterizing atmospheres. Each year of additional observations improves sensitivity, adds data, and narrows the uncertainty. The answer on TRAPPIST-1e. Does it have an atmosphere? And if so, what kind? Could come within this decade. And further out, in the 2040s, NASA is planning the Habitable Worlds Observatory, a telescope specifically designed to directly image Earth-sized planets in the habitable zones of nearby Sun-like stars, not inferred from a transit signal, not deduced from a gravitational wobble, actually imaged. a dot of reflected light from a planet's surface, and spectrographically analyzed for the chemical signatures of habitability: oxygen, water vapor, methane, ozone, the biosignatures of a living world. If an Earth-like planet exists within roughly 40 light-years, and it has a substantial atmosphere, the Habitable Worlds Observatory should be able to detect it and tentatively analyze it, and tell us whether it smells from 40 light-years away, like somewhere we might call home. That telescope could fly within our lifetimes, and what it finds, or doesn't find, will be the most important scientific result in human history. So, is there a planet where humans can live? Let's be honest about what we know and what we don't. Within our solar system, Mars is the most plausible option, but it would require centuries of engineering and technological development before anything resembling natural habitation was possible. It is a project for civilizations, not generations. Beyond our solar system, 45 rocky planets sit in the right zones around their stars. A few are close enough to be investigated meaningfully within our current century. Several have properties that, on paper, resemble Earth more closely than Mars does from orbit. And JUICE, right now, this year, is eliminating some candidates and keeping others alive. But what we have not yet found, not confirmed, not with certainty, is a planet we know has liquid water on its surface, a breathable atmosphere, and conditions where a human without a spacesuit could survive. That planet may exist. Given the sheer number of worlds out there, given what we know about how common rocky planets are in habitable zones, the statistical probability strongly suggests it does. The famous Drake equation, the framework for estimating the number of communicating civilizations, rests partly on the assumption that habitable planets are not rare. They may not be, but not rare in a galaxy of 400 billion stars is different from easy to find from 40 light-years away with current technology. We are early in this search, embarrassingly early. The history of exoplanet astronomy is barely 30 years old. The first confirmed exoplanet around a sun-like star was found in 1995. JUICE has been operating for less than 5 years. The Roman telescope hasn't even launched yet. We are at the very beginning. The question, is there any planet where humans can live, is really two questions. One is technical, and that one has a conditional answer. Not easily, not soon, not without technology that doesn't exist yet, but probably yes. Probably, somewhere in the galaxy, there is a world that would feel, in some meaningful sense, like home. The other is deeper. It asks what it means that we're asking at all. Every creature that has ever lived on Earth lived on Earth. Every bird that ever flew, every whale that ever sounded, every human that ever loved or built or dreamed, all of it happened here, on this one rocky planet, orbiting this one ordinary star, protected by this one improbable magnetic field, stabilized by this one large moon. And somewhere along the way, that planet produced something that wasn't content to stay, something that looked up at the stars and felt not just wonder, but longing, a pull toward the impossible distance, a compulsion to ask whether there was somewhere else, and to build the tools to look. We don't have the answer yet, but the fact that we're looking, with telescopes floating in the cold of space, with spectrographs measuring the chemistry of worlds 40 light-years away, with study after study narrowing the list from 6,000 down to 45, that search itself is one of the most extraordinary things our species has ever done. 45 worlds, 45 addresses. We don't know which ones are home. We may not find out in our lifetimes, but someone will. And when they do, When a telescope resolves the atmosphere of a rocky planet in a nearby star's habitable zone and finds oxygen and water and the unmistakable chemical signature of a living world, that day will be the most important day in the history of science, and perhaps the beginning of the most important chapter in the history of our species.